right. So I'm going to pick up where we left off from lecture 3 here. And this was all I had. I did not, this was the correct answer. We graphed it. We graphed the answer here to our problem, but I did not put it in interval notation. So in interval notation, the left starting point is 16. We would use a bracket because it's including it. And then the right is infinity. It goes off to infinity. So I did not include that in my answer for the last one. So I just wanted to pick up there. So let's look at another inequality. It looks like it starts off the same, but again, sometimes we end up with either contradictions or other things. So what does the algebra tell us about this? So if we start simplifying each side first, so we're going to simplify expressions. Always start with the expressions. So the left side, if we distribute the 2, we're going to have 8x. And then 2 times -3 is -6. Now the right side, we actually have a split. We have 2 terms. The term on the right will distribute the 3 to get 6x plus 3, multiplying 3 times 1. But then we want to combine terms together, and we're going to get, let me move this down a little bit. We're going to get 8x and then plus 3. So if we put this on the same level, we'll have 8x minus 6 and then greater than 8x plus 3. And remember with the equations, we think about our next step, which is isolate the variable term, right, on one side. That would zero out one of the 8x's, but if I do that to both sides, it kind of throws up a red flag, doesn't it? This is supposed to be a red flag, that my variable terms disappear. And we've seen that before. Variable terms are gone, right? And that doesn't mean we did our algebra incorrectly. That just means that we need to interpret what's left. So if you think about what's left, on the left side, we're going to have -6. And then on the right side, positive 3. And what we're left to do is interpret. If we have -6 is greater than 3, well, that's a false statement, right? So what the algebra is telling us is that this inequality, no matter what x term or whatever x value you plug in, you will never get a true statement. It will always be false. And this is what we called a contradiction before. But the solution, the answer, is actually no solution. Okay, sometimes they might call it the empty set. You might see the empty set. That looks like a circle with a line through it. Or it's a pair of brackets with nothing in it. So again, you might see that, but it's basically just saying that you do not have a solution. There's no solution. So does it always come out that way? Well, no, because if you think about what if, if we had something like this, what if we ended up with -6 is less than +3. So what if the question started out with a less than sign instead of a greater than sign? We wouldn't have done any algebra differently, but we would have got -6 is less than 3, which in this case is always true. So if it's always true, it's basically saying no matter what x value plug in, you will always get a true inequality. It's true for any value of x. So the answer to this would be all real numbers And in interval notation, it would be negative infinity to infinity. So this is kind of a new thing, but if you want to represent all real numbers with interval notation, it'd be from negative infinity to infinity. That includes all real numbers. The graph is just the whole number line, which really doesn't help us any. But again, we're left to interpret the inequality. So when our variable terms disappear, we're left with interpreting whether the inequality is true or whether it's false. Okay, if it's false, there's no solution. If it's true, then it's all real numbers. All right, so the last thing is an application of a linear inequality. And when we have applications, we want to be translating. We want to look for words that translate to inequalities. So when we're solving an application problem, I'm going to go through the same steps. So the first question, we want to translate, again, to algebra. So we're thinking about the first thing, what are we looking for? So if you look at the last thing, it says, what score does he need on the fifth exam test, on the fifth test, to have at least an 80 average? So we're going to let X equal the fifth exam score. So that's all we're looking for. Now, so there's no other quantity that we're looking for. So we're basically at step 3, which is what mathematical process involves the fifth test. Well, we have to understand what average is. What's an 80 average? And then we'll interpret the at least. So first of all, when we average, we add up all the numbers and divide by the number of numbers. So it's the sum of all tests divided by the number of tests to get the average. Okay, so if we want an average score of at least 80, so I would want to add up all the scores that I have. That'd be 71 plus 88 plus 78 plus 73. And then X is the last exam score. I do need to add that one. And then I'm going to divide all of it by 5. And that would be the average test score. And it has to be at least an 80. So if I were to compare that, it's not equal to 80. It says at least 80. So the at least 80 would mean that it's greater than or equal to 80. So again, it's just the wording in which we're asked. And I know sometimes it's like, well, the application like this, obviously if you score 80, I mean, if your average is 80, you're good. That's what he wants. But if you score higher than that, then you're going to average more than 80. So again, it's an inequality because of the wording, at least an 80. So, all right, so how do we solve this? We have a big fraction. This is one term on the left side. It's a big fraction. We could add up all these numbers, which we will. We'll add up all those numbers, but also, whoops. If we take and add up all these numbers here on top, we get 310 plus X divided by 5 is greater than or equal to 80. And then think of this as one term. So this is one term. So if I take this one term and multiply by 5, the factor in the denominator will cancel. So if I multiply both sides by 5, the denominator here will actually cancel. And I'm just left with the numerator, which is 310 plus X is greater than or equal to 480 times 5. And then to get x by itself, we can just subtract 310 from both sides and get x is greater than or equal to 90. So the last thing we want to do is just interpret our answer. So if x is greater than or equal to 90, that means that Bobby needs to score, or Bobby needs, maybe we could just say this, Bobby needs, well, we could say at least, because that's greater than or equal to at least 90 on his fifth exam. Or the fifth test. Okay. So that's it for section 2.5. Working with inequalities. This is really the only type of application with inequalities, because a lot of the inequalities, again, we could just solve them equal to 80, and then we would get x equals 90 and realize that if he scores more than 90 on the fifth exam, he would have at least an 80 average. It would be a little bit more.